Welcome to this module on predictive modeling with regression techniques. In the realm of data science, predictive modeling is a cornerstone for understanding and forecasting future outcomes. It allows us to build mathematical models that learn from historical data. Our focus today is on regression, a powerful set of statistical methods. Regression helps us model the relationship between a dependent variable and one or more independent variables. This enables us to make informed predictions and derive actionable insights. At its core, regression analysis seeks to estimate the relationship between variables. We aim to understand how changes in one or more independent variables influence a dependent variable. This relationship is often expressed through a mathematical equation. The dependent variable, also known as the response or target variable, is what we want to predict. Independent variables, or predictors, are the factors we use to make that prediction. Regression models quantify the strength and direction of these relationships. Simple linear regression is the most fundamental regression technique. It models the relationship between a single dependent variable and a single independent variable. This relationship is assumed to be linear. The model is represented by the equation y equals beta 0 plus beta 1x plus epsilon. Here, y is the dependent variable, x is the independent variable, beta 0 is the intercept, and beta 1 is the slope. Epsilon represents the error term, accounting for unexplained variance. Key assumptions underpin simple linear regression. These include linearity of the relationship, independence of errors, homoscedasticity, and normality of residuals. Violating these assumptions can compromise the validity of our model's inferences. Interpreting the coefficients is crucial. Beta 1 indicates the average change in y for a 1-unit increase in x, holding all else constant. Beta 0 represents the expected value of y when x is 0. Model fit is often assessed using R-squared, which measures the proportion of variance in the dependent variable explained by the model. P-values for coefficients help determine their statistical significance. A low p-value suggests that the predictor is significantly related to the response. Multiple linear regression extends simple linear regression to incorporate multiple independent variables. This allows for a more comprehensive understanding of complex relationships. The model considers the combined influence of several predictors on the dependent variable. The equation for multiple linear regression is y equals beta 0 plus beta 1x1 plus beta 2x2 and so on, up to beta pxp plus epsilon. Each beta coefficient now represents the change in y for a 1-unit increase in its corresponding x, while holding all other predictors constant. This is a critical distinction from simple linear regression. A significant challenge in multiple linear regression is multicollinearity. This occurs when independent variables are highly correlated with each other. Multicollinearity can inflate the variance of coefficient estimates, making them unstable and difficult to interpret. Addressing multicollinearity often involves techniques like variance inflation factor analysis or principal component analysis. Feature selection methods, such as forward selection, backward elimination, and stepwise regression, also help manage predictor sets. These methods aim to identify the most impactful subset of predictors for the model. While linear regression predicts continuous outcomes, logistic regression is designed for binary dependent variables. It is a powerful classification technique used when the outcome can take only two values, such as yes or no, true or false, or success or failure. Instead of predicting the outcome directly, logistic regression models the probability of the outcome belonging to a particular class. It uses a sigmoid function to transform the linear combination of predictors into a probability between 0 and 1. This probability can then be thresholded to assign a class label. The output of a logistic regression model can be interpreted in terms of odds ratios. An odds ratio indicates how much the odds of the outcome occurring change for a 1-unit increase in the independent variable. This provides a clear measure of association. Evaluating logistic regression models involves specific metrics. Accuracy, precision, recall, and F1 score are commonly used to assess classification performance. The receiver operating characteristic, or ROC curve, and area under the curve, or AUC, provide a comprehensive view of the model's discriminative power across various thresholds. Beyond the foundational techniques, several advanced regression concepts enhance modeling capabilities. Polynomial regression, for instance, allows us to model nonlinear relationships between variables. It achieves this by including polynomial terms of the independent variables in the linear model. Regularization techniques, such as ridge, lasso, and elastic net regression, are crucial for preventing overfitting. Overfitting occurs when a model learns the training data too well, performing poorly on unseen data. These methods add a penalty term to the loss function, shrinking coefficient estimates. Ridge regression adds an L2 penalty, which helps reduce the magnitude of coefficients. Lasso regression adds an L1 penalty, which can drive some coefficients exactly to zero, effectively performing feature selection. Elastic net combines both L1 and L2 penalties. Generalized linear models, or GLMs, provide a broader framework that encompasses linear and logistic regression. GLMs allow for dependent variables with error distribution models other than a normal distribution. This flexibility makes them suitable for a wider range of data types and outcomes. Statistical inference is paramount in regression analysis. It allows us to draw conclusions about a population based on sample data. Hypothesis testing for coefficients helps determine if a predictor has a statistically significant effect on the dependent variable. Confidence intervals for coefficients provide a range of plausible values for the true population parameter. These intervals quantify the uncertainty around our point estimates. A narrower interval indicates greater precision in our estimate. Distinguishing between predictive and explanatory modeling is important. Predictive models prioritize accurate forecasts, while explanatory models focus on understanding the underlying relationships. Both are valuable, depending on the research question. Translating model outputs into actionable insights is the ultimate goal. This involves communicating complex statistical findings in a clear, concise manner to stakeholders. Understanding the practical implications of coefficient values and model predictions drives informed decision-making. For example, a regression model predicting customer churn can identify key factors influencing churn. This allows businesses to develop targeted retention strategies. Similarly, a model predicting house prices can inform investment decisions. Robust model evaluation and validation are essential to ensure reliability. The train-test split is a standard practice, where data is divided into training and testing sets. The model is built on the training set and evaluated on the unseen test set to assess its generalization performance. Cross-validation, such as k-fold cross-validation, provides a more robust estimate of model performance. It involves partitioning the data into k subsets, training on k1 subsets, and validating on the remaining subset, repeating this process k times. This helps mitigate bias from a single train test split. Residual analysis is a critical diagnostic tool. Residuals are the differences between observed and predicted values. Plotting residuals against predicted values or independent variables can reveal patterns that indicate violations of model assumptions, such as nonlinearity or heteroscedasticity. Further model diagnostics include checking for influential points and outliers. These data points can disproportionately affect coefficient estimates and model fit. Identifying and appropriately handling them is crucial for model stability. In summary, predictive modeling with regression techniques offers a powerful toolkit for data scientists and statisticians. We have explored simple and multiple linear regression for continuous outcomes, and logistic regression for binary classification. We also touched upon advanced concepts like regularization and GLMs. Understanding the assumptions, interpreting coefficients, and rigorously evaluating models are key to building effective predictive solutions. By mastering these techniques, you can model real-world relationships, perform statistical inference, and derive actionable insights that drive value. This foundational knowledge is indispensable for anyone working with data to make predictions and inform decisions.